pressure-sensitive device measures depth as it sinks towards the seabed. The device is released from rest at the ocean surface and it sinks downwards. The water exerts a resistant force to oppose the motion. So we will refer to this again in the question, but basically it has its weight acting downwards like that, and there is a resistance force like so. So T is the time in seconds elapsed from release. Y, we can see on the diagram, is the displacement of the device relative to the surface. Notice that downwards is measured as negative, as we might expect. The velocity of the device, and A is the acceleration. The diagram shows that after 95 seconds, the device is 463.05 meters below the surface, i.e. y of 95 is negative 463.05. The acceleration of the device at any point in time is given by dv dt is negative 9.8 take away 2v. We want to calculate the acceleration of the device when the device is falling at a rate of 3 meters per second. So, remember downwards is negative, so we're after dv dt at negative 3, and so that's when v is negative 3, and that's negative 9.8, take away twice negative 3, so that's negative 9.8 plus 6, which is negative 3.8 meters per second squared. We're now told the graph of the acceleration dv dt is shown below, so it's against time. Explain two features of the graph of the acceleration referring to the differential equation dv dt is equal to negative 2v or the resistance force. Well, the first thing to note is, I guess, that in the initial acceleration is negative 9.8 meters per second squared, and that's because at the surface we have the weight, but the resistance is 0, so that's at the surface. So it's not actually submerged yet, so there would be no resistance. There's a couple of other things I'll mention. I know we're only supposed to do 2 for the marks, but acceleration is always negative. We can see that on the graph because it is below, and I would again consider the forces here, resistance and mg, and basically R cannot exceed the weight, really. And finally, asymptotes. We can see asymptotes. So as t tends to infinity, acceleration tends to 0, and that's because mg and r are greater, are closer, sorry, at greater depth. Show, using the separation of variables technique, that v of t is 4.9 e to the negative 2t take 1. Okay, so we have dv dt is negative 9.8 take away 2v. So that gives us 1 over 9.8 plus 2v dv is equal to negative 1 dt. So don't forget reverse chain, half log mod 9.8 plus 2v would be equal to negative t plus some constant. And so ln 9.8 plus 2v would be equal to negative 2t plus a constant. So 9.8 plus 2v would be equal to e to the negative 2t plus k, and that gives us 9.8 plus 2v is equal to e to the k e to the negative 2t. Now we know that it starts at the surface just being dropped, so v is 0 when t equals 0, and therefore e to the k is equal to 9.8. So we have 9.8 plus 2v is equal to 9.8 e to the negative 2t, and so 2v is going to be 9.8 e to the negative 2t, take away 9.8, so 2v is going to be 9.8 e to the negative 2t take 1, and therefore v is 4.9 e to the negative 2t take 1 as required. So, at a particular location, the device is released from rest at the surface of the ocean and falls until it strikes the seabed. If the device takes exactly 2 minutes and 30 seconds, that is 150 seconds, to hit the seabed, calculate the depth of the seabed at this location, correct to the nearest meter. And we know that the velocity is always negative, so it's not going to change direction at all. Therefore, we can just do this as the integral from 0 to 150 of v of t dt. That's 0 to 150 of our 4.9 e to the negative 2t take 1 that we found in the last part of the question. And if we calculate that, it's negative 732.55, which means to the nearest meter, the depth is 733 meters.